minimize, okay, W, H, but I have this, right? I can also write a function like this, right? Who said that I have to put the H in W? I can also split them, right? Then how do I minimize this? Well, then this is easy. I just gradient on F because there's no W here. So when I do gradient on F, I only need to care about gradient. If there's nothing on H here, then when I do gradient on H, I only need to care about this guy. So this is easy, right? But of course, there are sometimes something like this, W equal H. In this case, I'm saying they are the same thing. They're the same guy. So this is also the same as what? This is also the same as I have minimized fx plus gx, right? Because if W and H are the same guy, then it's the same as I only have one x variable, right? Let me tell you, in some situation, this one is hard to do. That means it's hard to optimize or minimize or maximize this guy. So you will do this. You split this x, so you have two functions. You name this my x1 and name this my x2, and you are saying that x1 and x2 have to be the same guy. So this is my x1, this is my x2. So now what I'm saying is that some application, this is hard to do, you may consider doing this. Okay? Or in some situation, your model, when you do some machine learning, you naturally get something like this, then you can consider this. They are equivalent, okay? Equivalent. So this is a basic idea. An example. Suppose I want to do this. Okay? This is x. So, how do you do this? Well, you say, oh, easy, I just do a gradient descent on this thing. But then you have a problem. This is L1 norm. It's not easy to differentiate. And even if you differentiate, you have lots of other issues. So, this is the example of this thing. You have a f, you have a g, you only have one x. Okay, but maybe not good. So now I'm going to convert to here. So I'm going to do the following. So now I will have my y. Okay, today is all about two variables. Okay, so now I talk about this. Okay, two variables. So I have ax minus b, 2 norm, plus what? Now this guy becomes y. cy minus d, 1 norm. But I have a new subjected to x equal y. So now I have this. So what's the advantage of this? When I do gradient descent, what I'm going to do? This is the only term on x. Of course, also here. So if I do gradient descent on x, I don't need to care about this guy. I can assume I don't see this guy. I only need what? I only have the following form. If I only on x, I call this x subproblem. The x subproblem is what? Minimize x subject to in a set C. This set C is a very funny set. It's a point set. X has to be equal to y. Okay? And then what? Right? And then what about my y subproblem? I only have to minimize this guy subject to what? My y is equal to x. I can replace this by x inside set C, and I can also replace this by y inside set C, right? We don't care about the expression right now. So this is old stuff, right? Project gradient descent on this, and then project onto this. Again, gradient descent, this is not differentiable, so you have to do subgradient, and then you project on this. So this is the same thing, and then you update this, bounce back and forth, then you will solve this problem. This may be easier than you update direct on this guy. Okay, so this is the trick. Again, today what I'm talking about. Previously, we talked about just this, and with a constraint. Now I'm talking about what happens if you have more than one term. You can try to do the old stuff, minimize in this form, but sometimes that is hard to do. For example, this is an example. Okay, trust me, this is hard to do. Okay, then what you can do? You can introduce something from mid-air. You split x into two variables. I call it w and h. They are both x. So they are both x. But this guy is only on one of the w. This guy is only on the h. So I split them. And when I split them, this is an example. On the x subproblem, I no longer need to care about this guy. I only have this. Everything in this block is simple. And on a y subproblem, I don't need to care about this. I only have this guy. Everything here is simple. So this is the idea. You have one variable, but you can artificially introduce another variable and with this in mind, okay? Then you get this thing. So this is the idea, okay? And now let me tell you, in general, how people deal with this. This is just a man-made story. It's not really what they do. The true way people do to handle this, again, this is just an example. We are not going to talk about the detail here. The way people solve this problem usually is not like this, but the following. And then you have x, and you also have y. Okay, same. You have the ax minus b plus. But here, I'm not going to say this is cy minus d. I'm going to say this is y1. And what? And I need the following constraint. The constraint is cx minus d equal y. Now I have this constraint. So this is slightly more complicated than this. So the idea is, if I have this, I can do the following, right? Mean fx plus hy, y is here. This is no x. Subject to what? My hy is gx. Yeah. So I have some function h and some function g that link them together. This is an example. Okay. So if the h and g are nice, then you can even say y is my h inverse gx, something like that. Or opposite, x is my g inverse hy. So this is the idea. Okay. Of course, we are not going to talk about this in detail because this actually has something called soft thresholding. But today, it's not about the exact model we are going to talk about. We are talking about how we solve this as a strategy. So this is the idea. So what are we going to do now is the following. I want to minimize. Okay, I only have an x variable. X is a vector. I want to minimize f1x plus f2x plus f3x plus fnx. Yeah, and make it simple, I divide everything by n. Alright, so it's like average. Okay, so what does it mean? You can think of it. Each f1, f2, f3, f4 is some function on x that the f is defined by some data. So this is like you have some process in machine learning. This is defined by data 1, this is defined by data 2, this is defined by data 3, this is defined by data n, something like that. And you want to find the x that fit the whole model very well to all data, something like this. This can be very difficult to solve. So how do we solve it? We are going to solve the same idea. You see previously I split it into two functions. Now I can split it into an n function. Okay, so what I'm going to do is like this, minimize. I have x1, x2, x3, blah 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 up to xn. Each of them have their own fx. Okay, so I have f1, x1, f2, x2, blah 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 up to fn, xn. Of course, I have to divide by n. Subject to what? I have a new constraint. All the x have to be equal. So x1 need to equal to x2 equal to x3 equal to x4 and okay, I can do this, right? So this is like the direct generalization of the previous case. Previously, what I have, okay, let me recap. Previously, I have this. Okay, I have this. I minimize. This is my f1, this is my f2. And what I do previously, I say that, okay, I have new y, okay. This is my x1, this is my x2. And then I have fx plus gy. And then I have x equal y, okay. Okay, now I have a bunch of them. I can do the same idea, right? I can do the same idea. So this is 2 for n equal to 2. This is for general n. And then what's the advantage? When I need to update x1, I only need to care about this guy. I don't care anything else. Of course, I also need to care about this. But this can be written as x1 in some set C. So I only have a simple form in the x1. And when I update x2, I only need to care about this guy and the rest I don't care. And then what I do? Update x1, then what? Update x2, update x3 until I update xn. And after I update all the xn, I go back to x1, x2, x3, x4. So this is a very general form. And usually, people don't write this clumsy notation. What they write this 1 over n summation fi xi. Okay? And similarly, they don't write this. They write 1 over n summation fi x. So this is the two things. I have x1, x2, x3, x4 up to xn, right? It's possible that each of the fi can be written as, let's say, phi ix plus psi ix. Right? Some case my fi may be very complicated. I split them into two parts. Then what you do, you replace this by y, and then you have another y1, y2, and yn. And you have another line. You can always do this. Or you can say this one is still too complicated. I keep splitting it, and then until, so this is like divide and conquer. You have a very big problem, very difficult to solve on x. What's the idea here? You split them into n problem. Each of them is easier. But it's possible after you split like this, it's still too complicated. Then you keep splitting it into two parts. Now you have a bunch of y. It's possible this is still complicated. Then you split into z, and then you split into w, and then you u, v, and then until at the point, it's very easy to solve. What's the drawback? Here, one variable. Now I have n variable. If I split it like this, I have 2n. If I split it 3n, 4n, 5n. So it's like what? This is very hard to solve. That means speed is slow or difficult. This is easier to solve. That means probably faster to solve, but you trade off space. You need to store so many things. So this is using space to trade off for speed. In other words, I'm just saying from here to here, it's also possible when you have a machine learning problem, you start from here, but you can also go back to here. So this is the idea, okay? So basically, this looks very complicated, but as long as you understand these two figures, then you understand the idea. This only have one variable, good, easy to solve. These have two variables, but you split them, so each a small problem is even more easier to solve, but you have to store two variables. If this is 1 million dimensional vector, then this is 2 million dimensional vector. Maybe it's very expensive to store 2 million variables at a time. Who knows? So this is the idea.